Hey everyone, Mr. Voppel here. Wait. Oh, sorry. My finger was on the camera. Mr. Voppel here. As you can see, I'm here in my underground bunker, awaiting out until the current apocalypse is over. Wherever you are, I hope you and your loved ones are safe and coronavirus free. Keep washing those hands. But onto the task at hand. You're here for your basic training. In this tutorial, I'm going to show you the ropes on how to do energy and work problems. You're going to prove that you have what it takes to tackle even the toughest of energy work problem tasks. I believe that you can do it. Now, before we begin, you're going to need two things. One, you're going to need your facts of physics. Go ahead and print out a copy to keep next to you while you do these problems. If you can't print it, go ahead and have a separate screen where you can access them at any time. Second, you're going to need a notebook, a piece of paper, to write out these problems as we do them so you can show me that you have what it takes. Ready? Go ahead and pause the video, get your stuff ready, and we'll continue after this. Alright, now that we've got that squared away, let's tackle our first problem. So what we've got here is a 10 kilogram weight, this blue box, and what we're going to do with this weight is we're going to take it and we're going to lift it up to some height above the ground there, some height, and we're going to say that the box is now, after we've lifted it, it's now at a height of 15 meters above the ground. And the question we're asking is how much work was done on this box to lift it those 15 meters into the air. Now to do this, no matter what our problem is with energy or work, we're going to solve it using the exact same three-step method, which you can see on your fact sheet. So go ahead, pull out your fact sheet, and let's see our 3 steps. It doesn't matter that this is a really simple problem. Maybe you can already figure it out on your own. No matter what problem we do, we're going to use these 3 steps because they're very helpful when we get to more complex problems later. Alright, so what's our first step here? Well, you can see our first step is we need to state where the object is initially and finally. Initially meaning at first, finally meaning at the end. So initially, where is the object before anything has happened to it? Well, it was back here down on the ground. We'll call this initially, this is number 1 here. It was on the ground. And finally, where did the object end up? Where we care, the moment that we care about. We're going to say we care about 2 here when it was raised to 15 meters. So in between there, from 1 to 2 is when it was being lifted. See how that works? So that's the first step. So now that we've done that, our second step is to draw an energy bar chart, which is one of these guys right here. There's a lot going on, but you can see there are basically 2 halves to this. So right here, there's initial, like we said before, and then there's the final. And then you can think about, I drew a dotted line right here. This area represents the during. So while whatever we care about is happening. So initial, during, and then final. So let's go ahead and write our states that we came up with for step 1. Initial was when it was on the ground. And then where it was for final was 15 meters in the air, or something that means that we understand what we're talking about. So you can pause the video or print out your own energy bar chart, take a second, get it ready, and then we'll continue after this. So go ahead and get that ready. And now the next thing we need to do is we need to draw a bar for each type of energy that the object possesses in these different states. So let's go through these and look and see if it has any of these types of energy. So when it's on the ground, does it have any kinetic energy? No, it does not have any kinetic energy. Why? Because kinetic energy requires motion. The object is not moving, it has no speed, there's no kinetic energy. Does it have gravitational potential energy? No. Gravitational potential energy requires height above the ground. It's on the ground, there's no height above its lowest point, which is the ground. There are no springs, so no spring potential energy here. Well, now let's look at after. After, does it have any kinetic energy? It is still not moving. We're not talking about while it's lifting, we're talking about after. So no. What about spring potential energy? No. The only thing that leaves us with is gravitational potential energy. Is it some height above its lowest point? Yes, we lifted it up. So it has to have some sort of gravitational potential energy. We'll draw a little bar here. The scaling's not important. I'm just drawing it so we know that there is some type of gravitational potential energy. So then, like our facts say below, we need to say why we know. We need to say how we know that there is some sort of gravitational potential energy. So this is really for you to understand in your own way. I might say, well, we know potential energy, gravitational is mgh, and we know that h is 15 meters. So we know, yes, it does have some sort of gravitational potential energy. So now the question you might be wondering is, well, hey, what about this idea of work? Work done by external forces. How can I know if it has any work done on it? Well, I'll answer that in a second, but let's move on to the last step, and it's going to become clear after this. So the third step is to write an equation based on these bars right here. Here's how you can think about it. We know that the energy before plus any work done by external forces is equal to the energy after. So you can think about it like this: kinetic energy before plus gravitational energy before plus spring and potential energy before plus any work done by external forces during the time period. Well, all of that has to equal kinetic, gravitational, and spring potential energy after. So let's write an equation based on that. Well, there's no kinetic, no gravitational, no spring before. Work external, I don't know about that. So let's go ahead and let's just leave that as a variable. Work done by external forces. We know that that has to equal the gravitational potential energy, which is equal to mgh, I know from my fact sheet. Awesome. So now that we've done that, we know, bam, physics is done. You did it. Now all we have to do is sort out the pieces. All right, so we know that the work done by external forces is equal to mgh. Mass is the mass of the object, which, as we remember, is 10 kilograms, times the gravitational field, which we know is 10 newtons per kilogram. 1 kilogram weighs 10 newtons. That's acceleration due to gravity, all the same thing. And the height above the lowest point, which we said was 15 meters. If we multiply those together, we get, kilograms will cancel, we get 1,500 Newton meters, and 1 Newton meter is equal to a joule. So we get 1,500 joules. Work and energy are both in terms of joules. So while we lifted this guy up off the ground, there was 1,500 joules of work done on the object. So now here's the question I want to ask you. Does this weight, now that it's been lifted up off the ground, does it have more energy now, or did it have more energy at the beginning, before we lifted it? So why don't you pause and think about that. So if we go back and we look at our energy bar chart, the answer becomes a little more clear. So we remember that before it had no energy, it had zero, no forms of energy, and then after it had this gravitational potential energy. So it had to have more energy after. So how did that happen? Well, what we know is that the bars on this side have to equal the bars on the other side. And so what had to have been done, like we said, was this work, which we calculated. So we can go to our energy bar chart now, and we can add in work. And we know that these two bars must equal each other. The work done by external forces equals the gravitational potential energy. And so one last thing that you might be wondering is there a way to know before going through all this there was or wasn't work done? Am I just kind of guessing and then I see at the end? No, we can know a lot of times because we know that work has to be done by external forces. If you look on your fact sheet, what are external forces versus internal forces? I'll give you a minute, pause it and take a look at that. And so what are these external forces? Well, one of them is an applied force. For instance, let's say that you took a book on your desk and you pushed it across the desk. You applied a force to it. That push is an applied force. Well, that book also is experiencing friction. Friction, we are not unfamiliar with. There you go, friction. That is an external force. The force of air resistance. Air resistance a lot of times we ignore, but if it is significant, it can be an applied force on an object. Tension, if we took a string and we pulled an object with that string, and normal force, let's say we've got a platform that's lifting something up, that's a normal force. It's also an applied force. Some of these are similar. So those are external forces. Internal forces that will not do work on a system are the force of gravity, the force of the earth pulling on something, and the force of a spring on an object. So there you have it. Your first challenge in basic training is complete. Go ahead and upload your results, and I'll see you soon. Bye.